Okay, hello everyone. Welcome to our webinar today. The webinar is about Slide2 and Slide3 software integrations and search methods. My name is Sina Javankhoshdel. I'm the product manager of Slide2 and Slide3 software. And today I have with me my friends and colleagues, Brigid Cami, who is the project manager of Slide2 and Slide3, and Dr. Terence, who is the senior engine developer for the Slide2 and Slide3 software. I'll just do the introduction and then I'll pass the presentation to these experts to talk about these two software. About rock science, we are the world leader of developing 2D and 3D innovative software packages for civil, mining, and geotechnical engineering. For over 25 years, we have built geotechnical tools used by over 10,000 users around the world. And this is our office in downtown Toronto. In this webinar today, we're going to talk about the major features that we developed in the Slide2 and Slide3 software in the year of 2022. Here is just a report of the versions that we released for both software. Slide2, we released 3 major updates with 3 minor updates. And for Slide3, we released 3 major updates as well. The next release of these two software will be at the same time in the next 2-3 weeks, the beginning of February, and that will conclude the development of the 2022 year. So briefly, I'll talk about the features that we developed in these two software. I just mentioned them. For Slide2, we had user-defined manufacturer library. We added a new support called helical anchors. We had new inputs for geosynthetics, coefficient of interaction, and friction factor. For the seepage results, now you can see the degree of saturations as well. We added a new material type to match a Slide3, which is C5 strength type. We worked a lot on the seamless integration of a Slide2 and a Slide3. We added a major option of RS log, our new logging management software, and the integration with the Slide2. So you can import RS log cross sections into a Slide2 software. We added a couple of features for the new generalized anisotropic strength type in a Slide2. 2 of them are already released, assign multiple anisotropic surfaces, and support blended properties with A and B angles. There is one that we recently added, import from Slide3, which we're going to talk about it in today's webinar, that will be released in February. For Slide3, the same as a Slide2, we have had so many new features. Generalized hook-Brown discrete function as a new material type. We had several improvements to the results, interpretation, and display options. We added user-defined manufacturer library to Slide3 as well. We changed all the material support and manufacturer library dialogues, and we improved the functionality of tension crack. As a major feature, similar to Slide2, we worked on the Slide2 and Slide3 seamless integration. We added a cool feature which is available in Rockfall 3D as well, which is texture mapping and train generator. One of the main and major features that we have released in years in a Slide3 is the Spline search method. And we're going to make it a default search in our next release, which is a very important option for searching the 3D analysis that Terence is going to talk about it today. We have 2 other features that we're going to release in February, the generalized anisotropy integration with the Slide2 software and Another major feature, which is the new weak layer algorithm. It's called binary optimizations that we're going to talk about this today as well. So in today's webinar, we have two parts in our presentation. First part, Terence is going to talk about new features in slide 3, including terrain generator and texture mapping. And then he's going to talk about his developments, basically new search methods, including spline search and binary optimizations for weak layer. In the second part, Brigid is going to talk about integrations between programs, including Generalized Anisotropic, Slide2 and Slide3, and integration of a Slide2 software with the RSLog software. I hope you enjoy today's webinar. I'll come back at the end to answer a couple of questions. Now I'm going to pass the presentation to Terence, and he's going to walk you through the new features in slide 3. Terence, please go ahead.
Awesome. Thanks, Sina, for the introduction. I'll be doing part 1, which will show a couple of new features that we developed last year in slide 3. The first thing I'll go over is the terrain generator and a similar feature called texture mapping. And essentially what it is you can now import surface geometry and satellite imagery into slide 3 using the new dialog. You can also apply image textures onto the entities in your model. So you get some really cool looking, geometric entities in your model that you can use and manipulate. For example, you can use drone imagery as well, and you can put those onto the surfaces that you create. I'm just going to do a real quick live demonstration of this. Let's go here. So again, let me know if you can't see my screen, but I have an instance of slide 3 open, and I'm just going to go in and import file, import terrain. And you can see here it asks you to choose a location in the world. You can simply just enter some coordinates here. I've already kind of determined which one I want to use. And this will be your world coordinates, so latitude, longitude. If you click set, it shows you where the region is. And then you can maybe choose the satellite imagery. You can change the dimensions of the imported area. And I'm just going to go ahead and click on assign map image as texture. So that'll actually import the image as well as the ground geometry. You can also preview it. So I'm just going to click preview here. There we go. Okay, so, oh, sorry. Yeah, so it generates a preview. If you like it, you can click on post process. Just wait for it to do that, and then you'll see here that it generates a preview of the geometry that I can look at. You'll notice here that there's a really high triangle count. The problem with if you have too many triangles in your model, it will take a lot longer to compute. So you want to limit this to as much as you need for the purpose of your analysis. So I don't want this many triangles. The default here, typically you'll get a good analysis of about 10,000 for most models. So I'm just going to click OK. This will simplify the triangulation without losing too much resolution, hopefully. And it should take us just a few more seconds here. Usually runs in less than a minute. And then after that's done, you can also repair any issues that there are with your geometry. We'll wait for that to finish. And it's done. So as you can see, we didn't really lose any significant resolution here. It's still satisfactory for the analysis I want. So I'm going to go ahead and click repair defects. It's just going to identify a few minor issues with the geometry, and you want to repair this, or else some people will have models that, maybe they could cause errors in the program. So click done, and then it'll actually save the image somewhere, typically in the folder that you save your project in. And then you can see here a terrain was generated. I'm going to reduce the transparency here to show the whole image. But as you can see, it looks really nice. We've even got the lighting on here. So what you can do is you can take this surface and you can manipulate it however you want. I'm just going to select the surface and create a external geometry, and this will create a volume inside your model, and it will be the extent of your model. So as you can see, we've created a volume that we can now use to analyze. One thing to note is that if you manipulate the geometry with the image in any way, the image will sometimes disappear. And to bring it back, you can always just reselect the surface. So what I'm going to do is click face selection, shift, and click on the mouse, shift left click. That'll select the surface again, and then I'm just going to go to geometry, triangulation tools, assign texture, and then bring the texture back in. You can also do this for drone imagery or any other image really, and you can assign it to any surface. You might have to rescale it if maybe you made a cut to the model or something. You might have to rescale it to fit, but if I haven't done anything here, so I'm just going to hit OK, and it should show. Let me just reduce the transparency here, so it should show the image again. So simple as that. That's how our new terrain generator works. I'm going to bring us back to presentation here. So the next part of, I guess my part, is the new search methods, the new exciting things that I developed as part of the engine in Slide3 last year. So the goal of this section is to introduce you to the methods for slip surface searching, particularly in Slide3, and also show you how to use our latest and most powerful method. So just a bit of a background for everyone to keep us all up to speed. A critical slip surface, is essentially it's the slip surface which has the lowest factor of safety, and this is the surface that will govern failure if it does occur in the slope. And theoretically, if the factor of safety is less than 1, then this implies that failure is imminent. So as you can see, it becomes very important to actually search for the lowest factor of safety in your model. Traditionally, 3D analysis in the literature and in the early stages of three-dimensional limited equilibrium software, people have only used spheres. And how this works is a sphere is defined using 4 parameters, the XYZ location of the center, and a radius. So as you can see, the portion of the sphere that goes underground forms the slip surface that will be analyzed. And then you can alter the values of these parameters, the X, Y, Z, and R, to change the slip surface and find the lowest factor of safety. So we can formulate this as an optimization problem. Essentially, it's basically we're trying to minimize the objective function of factor of safety by varying the 4 parameters here. And how do we solve this problem? Well, we use something called a meta-heuristic method. One example of a meta-heuristic method is particle swarm optimization. It's used very widely across multiple disciplines. And how it works is essentially the program spawns a number of particles, and these particles represent different slip surfaces, and these surfaces are generated more or less randomly, and each one represents either a sphere or an ellipsoid or whatever shape you choose to define for your analysis. And then these particles will actually communicate with each other, and they'll move around the solution space, and eventually they'll converge over a number of iterations into a location where the minimum factor of safety is found. So you can picture of it kind of like a swarm of bees moving around some sort of a domain, and they're all searching for an optimum location, and they're communicating within the swarm between each other to find the minimum. And we found that it works very well. So how do you use this is you can go to the slip surface options in the software, and you can, first of all, you can choose the shape of the slip surfaces that you want to use for this method. And so the spline search, the spline shape is the new method that we want to introduce in this webinar. Previously, you would have been able to select all of these other options, including the sphere and the ellipsoid. And then for the search method, you want to choose particle swarm. Do note that you can also choose a cuckoo search. A cuckoo search is another variant of these kind of swarm intelligence methods. But after some research over the last year, we did find that particle swarm is generally faster for the same number of iterations, especially for the spline search. And it's also conceptually simpler. It's so much more popular across every discipline than cuckoo search, so we decided we wanted to make it the default. And it's still similar in accuracy. And the last point is that it actually makes one of our new weak layer handling features possible. And so we're introducing a new weak layer handling feature called the Heuristic method, which I'll explain in a future slide within this webinar. And it just operates a lot faster than the previous one. And you can only use it when particle swarm is activated. So I guess the question is, why should we use this new spline method? And the answer to that is, without local optimization, the minimum sphere or ellipsoid that you'll find using a particle swarm search is most likely not going to represent the true critical slip surface. We know that in the real world, most slip surfaces are not actually purely ellipsoidal or spherical. We do also want to note that in terms of other softwares out there for limit equilibrium, slope stability, most people only really have ellipsoids at best. And so on here, I have sort of an example where the ellipsoid search found a minimum factor safety of 1.48, but the moment you alter that locally, which you can do in our program even before the spline search, you just turn the surface altering on. The moment you do that, it alters the surface and the factor safety goes down to 1.2. In fact, there are multiple locations in this model where the factor safety is a lot lower. So you can see that maybe a need for a more flexible surface has materialized, and that's exactly what we did with the new spline search. Just so everyone knows, a spline is essentially a set of points, weighted points, which kind of gravitationally pull the surface towards them. And as you manipulate these points, the surface becomes very flexible, and it can move to whatever you want. It's used in many different applications. And in this case, we're going to use these control points to push and pull our slip surface. to find the minimum factor of safety. So we're formulating the problem just like we did before, except this time our objective function is a function of 11 parameters. We describe these parameters in a little bit more detail in our publications. You'll see a reference to one of them in one of the next slides. But essentially, you don't want to keep your parameters too many. You don't want to have too many optimization parameters, or it just becomes too hard for the search to find anything. We found that 11 parameters was an okay amount, and it was able to find the surfaces fairly easily. And we're using the same particle swarm method here. We're just changing the parameters that are changed, that are altered during the search. And you can see here on the right, there's a sort of an example of a spline surface which was generated using this search. And for this particular model, we found that it actually made a really big difference compared to the ellipsoid search. And we ran, while we were testing this new method, we found that for over 80% of our test models, the spline search did find a lower factor of safety compared to the ellipsoid search. So this is done alone, this is prior to surface altering, which you can do on both of these surfaces. And it'll probably bring the result a little bit closer. So don't be afraid if you currently use ellipsoid. As long as your surface altering option is on, you should still get a decent result. It's just that the spline search is able to find a lower result a lot faster. And you probably still want to keep your surface altering option on, even if you do use the spline search. But anyway, so the surface altering, again, just to recap, is a very local optimization technique. So it takes the final surface that you get from your particle swarm, whether it's an ellipsoid or a spline, and it converts it into a spline if necessary, and then it locally alters that spline. So we've been using splines in Slide 3 ever since it was released. It's just that now we're improving the surface type options to include splines right off the bat. So now your search will be a lot faster and a lot more reliable as well. In this case, for this example, altering it further reduces it a little bit, maybe to about 0.98. And then the last thing I want to present here in terms of the theory is this new weak layer handling option. So just so everyone understands, let's consider a case where you have a slip surface and it touches two different weak layers, the red one here and the orange one. So the program can cut the slip surface to either of the weak layers or both, or none of them. And each case will give you a different factor of safety. The current options in our software to handle this are either you can select to always snap the slip surface to the highest weak layers. So that would mean cutting into both in this case. Or you can select the automatic case generation option, which considers every possible case and is very rigorous. But as you could imagine, if the number of weak layers gets very high, if there's a lot of weak layers in here, your program can become very slow if you use this option. So we developed a new method last year called the Heuristic method. It uses a form of particle swarm optimization to toggle these weak layers on and off based on the success rate of whether or not these weak layers actually produce a low, like a good solution for the factor of safety. That does this during the spline search or during the ellipsoid search. So it's a lot faster and performs very similarly to the rigorous option. So consider trying it out. It's going to be released in the upcoming release. And it's only available with particle swarm optimization. We published a couple of papers here showing how our spline search method does perform better than the ellipsoids for real world examples. So in this case, we have a coal mine. The model has some generalized anisotropic materials. It's got some joint planes in there, fairly complex geology. And the ellipsoid search alone was able to find 1.21 Spencer, whereas the spline search, because it's so much more flexible and it's able to warp the surface a little closer to what these joints look like, it was able to find a factor of safety of 1.11. And of course, if you add local surface altering to these results, it might be a little bit closer, but generally the spline search will still perform even after the surface altering. The spline search will more often than less give you a better factor of safety here. So if you're curious, you can read the paper here. Feel free to take a screenshot or something to get the reference. I have one small example to show here before I pass things on to Brigid. So let's suppose we wanted to analyze that terrain model that I imported earlier, and I want to compare the ellipsoid search versus the spline search, and with or without surface altering. So let me just switch to our model. So I have our model here. You notice that I've made a cut into the bigger square that I generated, and I created a model here. Let me just turn the transparency down a little. Turn it down all the way just to show you what it looks like. So as you can see, I've applied a texture to the top layer here. And there's two weak layers here in this model to simulate the faults in the region. And then as you can see in the materials, we have a bedding material, we have a joint material, and then in the middle, we have a generalized anisotropic function. So you can actually use this feature to define your joint orientations. And I've defined this for the yellow layer. So the yellow layer has 3 joints with dip and dip direction. And so essentially, if the slip surface is aligned with the joint direction, then it'll take on the joint material. But otherwise, it'll take on the bedding material, which is a lot stronger. And we have some basic generalized Hope Brown rock materials here. So that's what I've defined for the model. For the actual searching, I went to surfaces, slip surface options, and I selected the search method to be ellipsoidal. You can change this to spline if you want. You can change the weak layer handling depending on the cases you want to use. And then I've selected particle swarm here, and surface altering is toggled on. So I went ahead and ran the results already because we don't want to be sitting here waiting for a couple of minutes. And we were able to get a factor safety 1.17. You can kind of see here that it touches the yellow material just right at the bottom, but most of it's in the green material. One thing you can do is you can click on the Show All Surfaces button. And by doing this, it's actually able to show you all of the surfaces that were generated during the search. So you can just get an idea of the coverage that the search was able to generate for your model. If you have a really big model, you might want to separate it into different search boxes. But in this case, it looks like our coverage was okay. And you can even just isolate the surfaces and click on each one to view what it looks like. One thing that I really like to use is you can actually replicate a slip surface. So I'm going to take this one. This was the minimum ellipsoid that was generated during the search, actually. It'll show you the global min for no matter what you do, but the global min was actually a spline. But the minimum ellipsoid found during the search was 1.28. And if I click on create user defined, it'll show me what the ellipsoid looks like that was used to generate this result. And then you can use this as a user defined surface. Let's say you want to just analyze this again, you can go to here, click on user defined surfaces, and it'll only analyze the ellipsoid that you generated. That'll save you a lot of time if you're trying to replicate a result and save it to a new model. It's just so you don't have to run the entire search all over again. So that was the ellipsoid search. I'm going to go ahead and show us the results of the spline search. Again, you can go to surfaces, options, and then select the spline, maybe select heuristic weak layer handling to make it faster, or always snap to highest is pretty fast in this case. Select particle swarm, and then I've already computed the results again. So this is the result we got with splines. You have factor safety 1.15 after altering, and then before altering, if you click on show all surfaces, the particle swarm search was able to generate a minimum of 1.19. So this is the spline surfaces. I'm going to cancel this. So these are the spline surfaces. This is the spline surface that was generated from particle swarm alone. And it was already very close to the global minimum of 1.15. And so you can see that between the spline and the ellipsoid search, the results can be very different. If you look closely at the surface, it does kind of become a little flatter here at the bottom because it's trying to conform to the joint directions. Whereas with an ellipsoid, you can't really do that. No matter how I manipulate this ellipsoid and change its location or change its curvature, I can't really replicate the same degree of bending here that you can see in the spline surface. So that's kind of why the spline was able to generate a much lower result. And that concludes my example. So just a summary chart here, the ellipsoid search found a 1.28 factor safety, whereas the spline found a 1.19. After surface altering, the difference becomes a lot closer, but the spline search still wins out. So we found that this was the case for many of our test models while we were developing this feature. And that's pretty much it for me. If you have any questions, feel free to post them in the chat, and we'll do our best to answer them either at the end of the webinar or after via email. So I'll now pass the presentation over to Brigid.
Okay, so part two will focus on some important integrations that we've worked on recently. The first one is generalized anisotropic. So to start from the basics, an anisotropic material is one that has one strength in one direction and another strength in another direction. So for example, a jointed rock mass. The rock mass is strong, but along the joint, it's very weak. And the easiest way to understand this is with a simple 2D example. There are a lot of ways of modeling anisotropy in Slide 2 and Slide 3. The one I'm going to focus on is the generalized anisotropy strength type, which was in Slide 3 and was added to Slide 2 this past year. So the model we see on the right is one material. The yellow material is generalized anisotropic. There are two ways of defining the anisotropy in Slide 2, either with angle or with surface. So this is the dialog for angle. What this means is that the base material is this strong, which has a cohesion of 100, and the weak material is called weak, and it has a cohesion of 0. The angle of weak orientation is 45 degrees. So that means that if the slice base is 45 degrees, then it will take the strength from the weak material, which is 0. This 0 is the base cohesion. If it falls outside of that range, it'll take the cohesion from the strong material, which is 100. The meaning of A gives us a bit of leeway. So 45 plus minus A gets the weak material. And the meaning of B means that if the angle falls between 45 plus minus A and 45 plus minus B, then the strength is integrated between weak and strong. So for example, here the angle is 53, which falls between those A and B ranges, and the cohesion is interpolated. The other way of defining anisotropy is with the surface option. So this is exactly the same, except instead of typing in the angle, you select a surface. The surface is shown here, is the purple one. And basically the calculation and everything is exactly the same, except the angles of the slice bases are compared to the angle of the anisotropic surface. So for example here, the slice base is very similar to the closest point of the anisotropic surface, definitely within 5 degrees, which is A, and that's why the weak material is used. Up here, the slice base angle is very different from the anisotropic surface, so the strong material is used. This is the 100 cohesion. So that's anisotropy in a nutshell. How is it different in 3D? Basically, exact same idea. Instead of angle, we now have dip and dip direction, as you can see in the screenshot. And the anisotropic surface is three-dimensional. Now, the way we compare the way we determine if it falls on the weak orientation is, instead of comparing the angle of the slice base to the angle of the anisotropic surface, we compare the difference of the normal vector of the column base to the normal vector of the closest part of the anisotropic surface. This is sort of geometry jargon, but it basically comes out to the same thing, but in 3D. Okay, so a lot of our customers have asked us to be able to export 3D anisotropy to 2D. So how do you do that? Say you have this 3D model. It has two anisotropic surfaces shown here, these purple ones. And this is my 2D section, which I want to export to 2D. So I guess at first glance, when I export it, I would expect it to look something like this. So the gray lines are now my two-dimensional anisotropic surfaces. But is it as simple as that? Let's look at a very simple example. This is an extruded slope, and this gray plane is the anisotropic surface. Now let's say we take three 2D sections from here. One is here in the direction of failure, 2 is at a 45-degree angle, and 3 is orthogonal to the direction of failure. If we just cut this anisotropic plane, then our surfaces will look like this. So for the one that's in the direction of failure, for example, it's horizontal, and these guys are at different angles. Let's look at just the 2D section in the direction of failure. If we compute that model in 3D, we get a factor of safety of 1.4. If we then export it with our now horizontal anisotropic surface and compute it, we get a factor of safety of 0.6. And you can see that the factor of safety in 2D, the slip surface, is trying to conform to the horizontal anisotropic surface. The red line, meanwhile, is the 3D failure surface. So, of course, these are very different. Why is that? What we're doing here is the apparent dip method. So basically, we're saying that the 2D section doesn't know anything about the 3D anisotropy around it. So it just cuts the surface and it gets the result. Is there another way we can do this to get a result that's in agreement with our 3D result? Yes, there are two ways we can do it. So on the left, we have the apparent dip method. So again, this is where we just cut the anisotropic surface and bring it in. On the right, we have a method that considers the 3D anisotropy. So that means that this section knows that the anisotropy isn't just a horizontal plane, it's that 3D plane, which we defined. And how is this done in the computations? So on the left, the angle is just 0 degrees of anisotropy. On the right, we're actually bringing in the 3D orientations along this segment. So for example, we have the dip and dip direction on this chunk, the dip and dip direction on this chunk, and so on. So these are the two options we're giving the user when exporting anisotropy from slide 3 to slide 2. So probably you're wondering which one is correct, which one should you use? And unfortunately, there is no clear answer on that. No matter how you look at it, you're basically representing this 3D anisotropic surface on a 2D plane. So there's no correct way of doing it because it's not possible. So you need to assume something that's best for your model. And so you have to decide if you want to use the apparent dip method or the 3D anisotropy method. If you use the apparent dip method, you're cutting the anisotropic surface. And what you're saying is that you want to run a pure two-dimensional limit equilibrium analysis that doesn't know about the 3D anisotropic properties around it. If you consider the 3D anisotropy, you're saying that you have a 3D model and you want to take a 2D section out of it that knows about the 3D anisotropy around it so that you can get comparable results in 2D and 3D. So let's digest how this integration was done in an example. So I'll pull up my model. Okay, this is the model. The anisotropic surfaces are these two purple planes, and the anisotropic materials are this green one and this purple one, you can see there. And I've already computed this with Spline. And now I can look at my results. So I'm going to turn on display geometry as inset, which will let me see which materials this global minimum is intersecting. And then I'm going to lift the global minimum up. And I can see that it intersects both the green and the purple material, so both of the anisotropic materials. And the factor of safety is about 0.99. Now I will export this to slide 2. So first, let's look at the 2D section. I've already defined this. It's in the middle of the surface and in the direction of failure. While we're in this dialog, we've actually refined this dialog quite a bit and expanded the options for creating sections. So you can explore that in the next update. But for now, I'll just stick to my previously defined section. And I will now bring it to slide 2. Okay, so here is my section in 2D. Because these are 3D anisotropic surfaces, you'll see them as labeled as imported from slide 3. And if you double click on them, you can see exactly what we talked about. So this is segment 1, its dip and dip direction, segment 2, its dip and dip direction, and so on. Now let's look at the material properties. So the green and the purple were generalized anisotropic. Few things to note here. First, it says input type imported from slide 3. This is new, and this only appears if you're exporting from slide 3 to slide 2. And now we can look at our function. This looks exactly the same as we've seen, except now we have this 3D anisotropy handling option. So we have the option of considering the 3D anisotropy, which looks at the dip and dip direction, or consider apparent dip, which is if we just cut the anisotropic surface. So first, let's try the 3D anisotropy. Compute this. And one thing to note is that notice here that the anisotropic planes are in the direction of failure. So this is different from the simple example we looked at before. Now I'll open my results. Okay, so considering 3D anisotropy, factor of safety is about 0.91. The red line is the slide 3 surface. It's very similar to the slide 2 surface. Great. Now let's try it with the apparent dip method. So I'll switch this to apparent dip, and I'll switch my other function to apparent dip. And compute. So now this is basically exactly the same as if these were 2D anisotropic surfaces. And yeah, there's no knowledge of the 3D anisotropy around this 2D section. And I'll interpret. And the result is almost identical. The surfaces are almost identical, and the factor of safety is very similar. Now let me return to my presentation. So why is this so different? The simple example, which we saw in the PowerPoint, and as is shown in this image, had a sliding direction that was orthogonal to the direction of the anisotropic plane. So the difference between the two analysis options was huge. In the live demo, we had a sliding direction that was parallel to the anisotropic plane, so the difference between the two options was negligible. So again, it'll be your choice whether you want to do a pure 2D analysis or whether you want to consider the 3D anisotropy around it. Depending on the orientation of anisotropy, it might make a big difference. And just a couple of additional notes. As I mentioned, you'll only see that imported from 3D option in slide 2 if you are exporting your generalized anisotropic model from slide 3 to slide 2. You can't define that organically. And if you have a very narrow A and B, it'll be harder for the 2D section to fall in that range. So for best comparison results, we would suggest that you use full interpolation, A equals 0, B equals 90. Okay, the next important integration is RSlog in slide 2. RSlog is our newest software. It's a web-based borehole log management software. Here are some of the important features. And for this one, I'll dive right into the example. So let me open my browser. So this one is online. Log in. I won't go too in depth into the RSlog features. There's a lot of content for this on our YouTube channel. But this is the dashboard. I'll go to my projects. This is the list of projects. This is the one I have open right now. It's highlighted, slide 2 cross-section. And I'll go to test holes. This project has 3 test holes. And then I will go to cross-section. This is where the slide 2 integration comes in. So here, these are the 3 test holes. The way I would define a cross-section is by clicking between one and the other. And then I can name this, for example, test section. And open it. And then here I would be able to define my cross-section geometry. So for example, these are the test holes, so we can see the materials in the test holes. And I can just easily draw the cross-section, assign my material to it, and so on. For the sake of the example, I have a predefined section, which is shown here. To bring this into slide 2, I have 2 options. I can go to export and export rock science section to do it manually, or open a fresh slide 2. or I can do it with this button, import RSLog cross-section. And with this, I can log in directly into my account. If I were to do it manually, I would use this import option, but I will not. And here I see my list of projects. So I'll select Slide 2 cross-section. There's some information here. And here are my 2 sections. So I'll import this one. This is telling me that the unit system is different between Slide and RSLog, so it's asking if I want to change it, and I'm saying yes. And now I have my soil profile. So this by default imports as a soil profile. If you wanted it to import it directly as a slope, you can do that. And now I'm just going to, all I have to do now is cut the geometry. So this is a soil profile in soil profile mode. To cut the slope out of it, I would select add external boundary, add external as polyline, and define enhancement slope. If you're to do it manually, you can of course input the coordinates. And then if I look at the materials, the integration has brought in my material names and my material colors. So the last step I would have to take is input my strength parameters. Okay, that's the RSLog integration. So to recap, this is our newest software, web-based borehole log management. Right now it integrates with Slide2 and Slide3. And you can also import other file types to RSLog, such as GINT, Excel, DIGS, and AGS. There's a promotion right now. If you have an existing Slide2 or Slide3 license, you can get an extended trial of RSLog, which would last until March 31st. And now I'll pass it back to Sina.
Thanks, Brigid. To conclude the webinar, these are the topics that my colleagues, they talked about several cool features that we developed in Slide2 and Slide3. Terrain generator texture mapping and spline search and binary optimization in Slide3. Generalized anisotropy in Slide3 and Slide2 and RSLog integration in Slide2. I hope you guys try these and let us know your feedbacks. Interesting news, probably a lot of you guys know about it. We have our second international conference in Toronto in person in April 2023 from April 24th to 26th. We have received over 215 abstracts and we are waiting for the papers to come. Please join us in this conference. This is going to be a real multinational conference and in person in Toronto. So we are looking forward to seeing all you guys in the conference. We have 3 courses as well at the conference, slope stability settlement and tailing dam courses that you can register for the courses as well. So we are done. We have 4 minutes for the Q&A section. There are a lot of questions. I try to type all the questions and answer them. The last one that I didn't answer, I'm going to answer it here. Is there any PDF for the features of our software? Everything about rock science software, you can find it online on our website. So you don't need a PDF. Everything is online. You can just search for the features that you are interested, and you can find the articles related. The other questions that they were interesting, it was like, for example, if you can import 3D anisotropy from RS3 to Slide2 or not. This integration, the current generalized anisotropy integration, is only available between a Slide3 and a Slide2. However, you can always bring your, because a Slide3 and RS3, they share a lot of things and they are integrated. So you can always bring your 3D anisotropy surfaces from RS3 to a Slide3 and then take a section cut as Brigid showed, and you can have this option in a Slide2 look at the anisotropy in a Slide2 as well. this presentation, we're not going to share the files of the presentation, but the video will be available on Rock Science website, YouTube channel very soon. The other technical questions would be, does a Slide3 have the capability to quantify depth of failure surfaces? Yes. We added a new option last year, which was column depth option. You can look at the contours of the column depth, which shows the depth of a slip surface at different locations. Also, we have a project report that after the report generator, that after the analysis, you can look at a lot of information, including the slip surfaces, the depths of slip surfaces, volumes, and this kind of information in the report generator as well. The other question is that is it possible to use a Slide2 and a Slide3 for to estimate an extent of a zone with a specific factor of safety? That's a very good question. There are different ways. In a Slide2, you can use the filter option to look at the range of the factor of safety that you're interested in. A Slide3, we have two options. Either you can look at all surfaces and filter the surfaces, or you can use a safety map, and you can, in the safety map, you can look at the specific regions. You can define the specific regions to look at the safety map of the factor of safety, which is the region of interest for you. I believe we answered all other questions. So please feel free to contact us if you have any other questions. We're going to send you these questions with the answers via email as well. And thanks again for joining us in this webinar today. And please look at your Slide2 and Slide3 software. You're going to see our new update in the next 2-3 weeks. Thank you so much, and have a great day or night wherever you are.